non-interacting particles. So if you recall, we said that the limitation of Boltzmann statistics, which we started from Boltzmann statistics, and the limitation of Boltzmann statistics was that so limitation of Boltzmann statistics was that particles were non-interacting. Particles were non-interacting. And that is why the total energy of the system we could write as sum over individual particle energy. So this is good for a dilute or an ideal gas system. But here we are more interested in a biological system or a dense liquid system where particles are very much interacting, and therefore the Boltzmann statistics will not work well there, and therefore we move on to the ensemble approach. And in the ensemble approach, we got the partition function Q as drn. We have another integration over the momentum P, and then we had e to the power minus h is the Hamiltonian divided by Boltzmann constant Kb times temperature. So this is the partition function. So here are few things we need to remember is that so a couple of things we need to remember is that now we have shifted to the classical regime, and we are treating the classical systems here because the biomolecules or the liquid state of a system is basically a large systems. They are large systems, and therefore large systems cannot be tackled quantum mechanically. And therefore, from now onwards, whenever we'll be talking about the biological molecules, thermodynamics or the statistical thermodynamics of biological system, we are basically in the classical regime, and we'll be talking about classical mechanics, not the quantum mechanics. And the other thing we need to remember is that like we written Hamiltonian, which is a function of R and P, where R is the coordinates, R is a coordinate of a particle, and P is the momenta. So here the R and P they represent the nucleus of the atom, and to have this, we have here introduced or we have taken care a very important approximation called Born-Oppenheimer approximation. So Born-Oppenheimer approximation assumes that in an atom, the nucleus, the motion of the nucleus and the motion of the electrons are independent, and therefore, so that is one, that the motion of the nucleus and the motion of the electrons are independent, and since the electrons, they move much faster, they basically move so fast, they have a electronic cloud around the nucleus, and therefore the electronic motion can be averaged out. So in classical mechanics, all you have to do is basically look at the motion of the nucleus alone, because the motion of the electrons is so fast that the motion of the electrons can be averaged out, and you just look at the motion of the nucleus. And that's a von Oppenheimer approximation which we have implemented here, and therefore the R and P, what you see here in the partition function and in the Hamiltonian, they are basically the position and the momenta of the nucleus of the atoms. All right, so so we have to introduce the interactions among the particles in this regime for the biological systems. And how do we do that? So you saw that my partition function Q had partition function is a function of Hamiltonian Rn Pn Kb by T. So we have this Hamiltonian here, and what is this Hamiltonian? So Hamiltonian, or which is a function of R and P, represent the total energy of the system, and total energy of the system is the sum of kinetic energy and the sum of the potential energy. Kinetic energy is a function of P, and the potential energy is a function of R. Now, what is Kp? The kinetic energy. So, kinetic energy is basically the Kp, which is nothing but sum over I, is if the number of particles is n. So, this is nothing but half mi vi square, where m is the mass and vi is the velocity, which is nothing but sum over I is equal to 1 to n pi square by 2 mi, where pi is the momenta, and that's why k is a function of momenta. And if you derive it, this comes out to be 3 by 2 n kBt. N is total number of particles, kb is the Boltzmann constant, and T is the temperature. So, as you see, the kinetic energy is constant. N is constant, Boltzmann constant, and T temperature is fixed for a system. So, the kinetic energy is fixed. The potential energy U, which is a function of R, this basically contains the information about the interparticle interactions. So, UR contains information about the interparticle interactions. How? Because U, your total U, the potential energy, it basically is a function of particle 1, is a function of particle 2, is a function of particle 3, function of particle 4, and is a function of all the nth particle. And this total U which we can write as U as R, therefore can be written as sum over ith particle, jth particle. So, sum over U2 Ri Rj, where I is the Ri is the coordinates of ith particle, j is the coordinates of jth particle, and U2 is basically the interaction of ith particle with the jth particle. And so, this is called pair interaction, because here two particles are involved, I and j. So, here I the first sum is over I and the second sum is over j. So, I goes from 1 to okay, we'll come to this limit. So, here basically the first sum is over I, the second sum is over j, but this has to be, j has to be less than I. So, I less than j. So, this is two body interactions plus total U also contains three body interactions. This is I, this is j, this is k, and this we represent as U3 Ri Rj Rk. Likewise, it will have all higher body interactions. If the particles are contained in a container and the wall of the box is influencing the particle motion, then you also have a term here which should be sum over I U1 Ri, which is a single body interactions where the wall is influencing the motion of each particle. So, that you can say a one body interaction if the box, if the container is influencing the motion of the particles. Apart from this, the two body interactions here. So, total energy, total potential energy now is a sum of one body interactions, two body interactions, three body interactions, and the higher body interactions. So, what do you mean by this two body and three body interaction? What is the definition of three body interactions? Let's look at here. So, this is our box which contains these particles, and so two body interaction is the interaction between this and this, or this and this. This is the two body interactions. But the particle here and the particle here, they also can have interactions through this particle. So, I am talking about interaction of this to this through this. So, this is the three body interactions. We can have four body interactions if particles are lying very close. So, this particle and this particle can have interaction through the intermediate particles, and this is called the four body interactions. So, in reality, we have many kinds of interaction of this container wall on the particles, which is this one body interaction. We can have paired interaction between each pair of particles, which is here. Then we have 3 body interaction between particle 1, 2 and 3, which is 3 body interactions. We can have 4 body interactions between 1, 2, 3 and 4, and we can have many higher body interactions. But if you look at it carefully, the pair interactions will have the largest contribution, because pair is basically the particles find to each other more closely than the 3 body or 4 body interactions. For practical purposes, the total U, which is a function of R, very often is written as U1 R sum over I Ri plus I would change this symbol to very often written as, so this is I, this is J, very often written as U2 Ri Rj. These are vectors. So what is the limit of I and j here? So I is equal to 1 to n minus 1 and j is equal to I plus 1 to n, or j has to be always greater than I, so that we don't count the same pair interaction twice. When we put this in equality, we make sure that we don't count the same interaction twice. For example, if I have a system of 4 particles, total number of pair interactions we have 1, 2, 1, 3, 1, 4. Then we have 2, 3, 2, 4, and then we have 3, 4. These are the distinct interactions. We can also consider 2, 1, but 1, 2 and 2, 1 are the same interactions. Likewise, 1, 3 and 3, 1 are the same interactions. 4, 1 and 1, 4 are the 4 interactions. So if we count 1, 2 and 2, 1, so that means we are overcounting the number of interactions, and therefore we should not overcount. And because and to overcome that, the overcounting, we have put this in equality where j is more than I. J is exactly I plus 1 to n, and I is equal to 1 to n minus 1. Okay, so that's the definition of pair interactions. And since pair interactions contribute majorly, this is not a bad approximation that my total U is sum over one body interaction if the particle wall is influencing the particles, plus the pair interactions between the particles. We can easily omit the 3 body, 4 body and the higher body interactions. There is also a way when we model this pair potentials, we also can make this pair potential better by looking at the experimental data, and by using the experimental data we can improve this pair potential, which to some extent or indirectly incorporate the higher body interaction terms. And in that case, this U2 is called the U effective pair potential, where this is called effective pair potential. So, what is effective pair potential? Effective pair potential is something which is better than the regular pair potential. In effective pair potential, the interactions of higher body terms have been indirectly incorporated into the U2, and how we can incorporate the higher body influence into U2, that will be clear to you shortly when I write some of the expressions of these U2s. So, because of this effective pair potential, the definition of U, total U, in terms of effective pair potential is not a bad approximation, and it gives a pretty good match with experimental data. Okay, so as you see, this effective pair potential basically talks about the interparticle interactions. That is what we are talking about here, that in Boltzmann statistics, since we missed the interparticle interactions, we need to introduce the interparticle interactions in the liquid system or the biological systems, and therefore we have introduced the interparticle interactions through the potential energy. And my total potential energy of the system is nothing but sum over all the pair interactions. Now, so if you have this effective pair potential known, then we have a good hand on U, and therefore we have a good hand on H, the Hamiltonian, because kinetic energy is constant, and therefore we have a good hand on the partition function. Once we have the partition function known, we know everything about the system. We know every thermodynamic quantity of the system.